Hello, good afternoon. Can you hear me?
Good afternoon, Ajahn. We can hear you.
Okay. So today I will going to continue about the deep neural network. Okay, but before that, I will also do the review about the uh, back propagation in the artificial neural network. Okay, and then after that, I will discuss about what is a deep neural network. Okay, basically, I will discuss about starting from the deep learning. Okay, and then after that, I will continue about the deep neural network. Okay, and then for this course, okay, I will continue until next week. Okay, so that's why please keep in mind that there is one more lecture in the next week. Okay, and then for tomorrow, I will upload it the assignments. Okay, I think the assignment 4 or 5. I'm not sure. Okay, and then please also finish that assignment before the semester. Okay, but that assignment is only about the neural network. Okay, not too much about the deep neural network. Okay, like this. Okay, let's start. Okay, so today I will discuss about. Firstly, I will recap about the cost functions and gradients because last week I could not cover the whole things. Okay, because of the time limitation. But today I will recap it again. Okay, and then after that I will discuss about what is a deep learning and this architecture like the deep neural network. Okay, and then actually there are many deep neural network algorithm. Okay, but in here I will for just today I will just cover about the CNNs, convolutional neural network. Okay, and then next week I will cover about the RNN and also there's another deep neural network. It's we call it a GAN. Okay, generated adversary network. Okay, so anyway, let's start today. Okay, let's go. So this is about the back propagation, okay, of the neural network. Okay, that is also applied in the deep neural network. Okay, so I have already discussed about this figure twice. Okay, basically in the back propagation, because firstly you have to calculate the forward propagation. Okay, for the forward propagation, okay, you have to use or you have to do that algorithm. Okay, in the training and as well as in the real predictions, or we call it a fitting. Okay, just a minute. Okay, but in the training, okay, we have to do another way of the propagation. Okay, forward is mean we go from here to here, this direction. Okay, we have the input. Okay, and then we multiply with each weight and then calculate the derivation functions and then transfer to the next layer and next layer like this, and then we generate the output. Okay, so we got the output like this. Okay, but in the neural network, okay, the main idea is the weight. Okay, we have to uh, find the weight. Okay, based on that weight, okay, the network, the performance of the network will be different. Okay, and then we have to find the weight that gives you the best performance. Okay, the best performance is mean we call it less error. Okay, so how we can update or how we can adjust the weight, okay, in the neural network is by using this backward or back propagations. Okay, basically it's calculate the gradient computations. Okay, gradient is being actually partial derivative of that error, okay, divided by whatever weight you want to update it. Okay, so for that gradients, okay, before we talk about the gradients, okay, let's talk about the error. Okay, in the backward propagation, okay, what we have to do is we have to update this weight, okay, based on this error. Okay, but the error we can calculate at the end is depend on the final layer, the output layer. Okay, but the output, the error at the each output layer, okay, is need to transfer that to the other layer, like the hidden layer, okay, need to transfer back to that layer. Okay, and then after that, based on that transfer error, okay, backward transfer error, we have to adjust the weight. Okay, but before we talk about how to adjust the weights, okay, we have to talk about how to transfer back the error. Okay, so basically in here, okay, basically this is the output layer. Okay, this two is a hidden layer like this. Okay, this two is a hidden layer, and then from the output layer we have to calculate the output. Okay, so that we call is a predict output. Okay, y. Okay, and then let's assign that y as a here. Okay, and then in here, okay, we have, this is just a training process. Okay, so that's why we have the data set that is been for each input data. We also have the no target data. Okay, so that's why the output of the layer, the output of the output layer, we call as a. Okay, and also the target output or our desired output. Okay, that we assign as a y in here. Okay, so that's why the a in here is mean the output or our predict value, and then this y is mean our target or desired output. Okay, and then we can calculate the error in here. Okay, the error is mean this is the output from the output layer, and this is our desired output. So the error in here is mean a minus y. A is mean the output from our model. Y is mean our desired output. Okay, and then the difference between that one we call as the error. Okay, so in this case, let's say in this ASMR, we have 1, 2, 3, 4, 4 output node or neutral. And then each of them is where generated the respective output 1, 2, 3. And then we will have that target output 1, 2, 3 like this. And then we can define the difference between each pair. Okay. And then that error, okay, in this case, we assign as a sigma. Okay, so in this case, if we have the 4, okay, actually it's a federal. Okay, we have 1, 2, something like that. Okay, and then each of them we calculated from a1 minus y1, a2 minus y2 like this. Okay, so this is mean the error from the output layer. Okay, and then if we want to transfer that error, okay, this error to the previous layer. Okay, this is layer 3. Okay, in here, what we have to do is to get the output in here. Okay, so actually in this case we have the two calculation. Okay, first we have to calculate the z. Okay, z is summation of, okay, w from the layer 3. Okay, with the output from layer 3. This is mean the output from here, like this. Okay, this is C. Okay, and then after that, for this C, okay, we pass through the activation functions like this. Okay, so if we want to calculate the error appear in here, here, okay, what we have to do is we have to, this is mean the error, okay, this is the error, okay, is passed from here to here, okay, but we need to calculate this error. The error appear in this each node, okay, that can be calculated. This error from the output multiplied with, okay, this one is actually gradients or partial derivative of the activation function in each of these nodes. Okay, that one. Okay, and multiply with respective weight, the weight in here, the weight in here. Okay, because this error is combination of the output multiplied with weight in here, output multiplied with weight here, like this. Okay, so that's why for the error 3, okay, this error have to multiply with the respective weight, and then we will get this error 3. Error 3 is means sigma 3 is mean the error appear in this node. Okay, and then also we have to transfer that one back to the previous one also. Okay, and then it's have to calculate the same formula like previous one. Okay, this is mean the error from the node before. Okay, and this is the activation function. Okay, partial derivative of the activation function at that layer multiplied with that respective node. Okay, like this. Okay, so this is the formula, and then later on I will show you the demonstration how is how we can calculate that one. Okay, so before we talk about this gradient calculation, okay, we have to calculate the gradients. Okay, the gradient is mean actually the changes. Okay, am I right? The changes. Okay, changes of what? Okay, in this case, the gradient is mean okay, if we change each respective weight W, okay, because in the neural network, you have many weight value in the each layer and also in the each node. Okay, if we change one value of the weight, okay, and how is the changes of the error? Okay, how is the changes of error? We have to check it. Okay, that we call it a gradient. Okay, and then based on that one, we have to update that weight. Okay, if error is large or negative or positive, we have to increase or decrease that weight. Okay, so before we calculate that gradients, okay, we need to define how we can calculate this error. Okay, and how this error is being taught about the performance of your model. Okay, we have to define that error first. Okay, that error can be defined by using the cost functions. Okay, in if you look at many textbook about the neural network or machine learning or optimizations, okay, there are another function, okay, that called is a loss function. Okay, these two are can be interchanged, okay, but same textbook, okay, is referred that this one is referred to the is neutral or is not at the output. Okay, this one is referred to the whole system error like this. Okay, so That's why before we talk about the gradients, okay, we have to talk about the cost function, okay, and it's very important in the performance of the neural network. Okay, so it's used by the engineer to determine how effectively the neural network can perform send tests accurately. Okay, uh, okay, so this is our cost functions. Okay, actually, the cost function is not the function of the weight. Okay, so please let me define this one here. Okay, this J is mean the cost functions. Okay, and then we want to define that one with the function of weight. Okay, weight in here is mean actually is a parameter. Okay, the parameter we want to find is this mean the weight we want to update or we want to find. Okay, the best parameter is what gives you the minimum cost or minimum error. Okay, so we define like this. Okay, but actually the cost function is defined in terms of this is like A, I just mentioned previously. A is the predict, okay, or output of the network, okay, output of the network. And Y is our target or desired output, okay. Actually, we have to define like this, but for the A, okay, if you look at the last week lecture, okay, A is defined with a activation function at the input of C, okay, and then what is the C? C is being weight multiplied with input, okay, plus B, or maybe we just write off WH, okay, and then maybe you have to put H, one more element as in one, and then this B can be combined with W, okay. So anyway, this is C. So the C is actually the function of the W, okay. So that's why if we want to change or if we want to update this one, that requires a parameter, okay, we can write down that cost function as a J omega, okay, but actually it is the function of A and Y. But A is the function of that one, like this, okay, so that's why please keep in mind about that one, okay, and then if we consider, okay, for this cost function, actually we use as a error as a output layer, okay, so this like this. Okay, but in the simple case, the error is with the difference between that one. Okay, but actually when we do the derivative functions, okay, we do find that that one, okay, is going to be very similar to that, just a difference. Okay, and then in this case, this one is me. Okay, let me write down this L first. L is AY. Okay, and then if we differentiate this one with A, okay, we have to write down like this. Sorry, this one, sorry, I made a mistake. This one should be C. Okay. With respect to A, okay, and then for our A, okay, we have to redifferentiate with the C like this. Okay, and then after that, from the C, we can continue. Okay, because the C is this one. Okay, so that one, okay, that one we assign as an error. Okay, and then by checking this error, okay, or by using that error, okay, and transferring to the back, okay, we can update the weight and then check the changes, and based on the changes, okay, changes is mean that error changes, we will update it again and again. Okay, that is mean that call functions. Okay, basically for the cost function, okay, there are various types of the cost function, okay, especially in the machine learning. Okay, but those cost function also apply in the neural network because the neural network is subset of the machine learning. Okay, so in here, let me there are many cost function. It depends on the whether you are going to do the classifications or you're going to do the regression. Okay, classification is mean to classify one or two or three classes. Regression is mean like for the linear regression. Okay, we predict, okay, the real value like this. Okay, normally for the let me start with this regressions. Okay, it's normally use a square error function. Okay, or some cases it's use a absolute dot or error. Okay, and next one is a or maybe sometimes we call it a loss function. Loss of cost. Loss function. Okay, but let me call as a loss function first. Okay, this is also loss. Okay, and then in here, let me refer that loss function is being depend on the is referred to the is no is output no. The output dot is output no. The cost is being the whole network. Okay, for the classification also, we can apply linear cross entropy. Okay, and another one is a categorical if you have many. And another one is because the loss function. Okay, so from that, okay, for the regression, okay, let me only show you these equations, okay. So that one is quite simple, okay. That is mean the square error function or equation, okay. That is mean, okay, let's say if we have only one, okay, if we have only one, we can calculate that loss or that error, okay, or that error, okay, it's depend on the a I, let's see, minus yi square, okay, like this. And then if you have, okay, many symbol, okay, for the cost functions, okay, it's nothing, it's just a average of the summation of I is equal to 1 to n, okay, we have to calculate like this. Okay, so this is the cost function. Cost function is just the average, okay, of the east log function, because east log function is depend on the east. Sorry, I made a mistake. This is not, no, this is the east sample. Okay, and cost is mean the whole. The whole sample. Sorry about that. Okay. So this n is mean the number of sample like this. Okay. But as I mentioned that, okay, you can also use this one as a cost function also. Okay. The difference like this. So this is the cost function. Okay. So it can be defined like j omega. Okay. And then if we assume that there's only one symbol, okay, so we can ignore this one. Okay, so this is mean we have only ai minus yi square. Okay, like this. This is j omega. And then if we find partial derivative of this one with respect to just a, okay, this ai, this a is will be equal to 2ai minus yi, like this. Okay, so this is being, if this is the constant, if you ignore it, so this is being just ai minus yi. So it will be the same as the one in the previous formula. Okay, like here. Okay, and another cost function. Okay, so in this case, if your model or if your function is not complex, okay, it will be like this. It's a converse. Okay, and then converse is mean this is j omega, and this is the omega, so not omega, sorry, w, and this is the w. Okay, and what you have to do is you have to change this w. Okay, w is weight, okay, or the weight, and then find this value. Okay, and then this is our desired w, because in this case this j w is a smallest or minimum. Okay, that is mean how to find the optimal W to give the best performance of the system. Okay, but in some cases, okay, because this A is G, Z, and then Z, if you have many weight, okay, and then some cases, okay, it will be not the compass, okay, it will be like that. Okay, there are many okay, many miniman, okay, but this and this we call as a local. This is a local, okay, because this is the minimum between only this range. This is the minimum between this range, okay, and what we need to find is the minimum in this range, okay. So that's why in the classification, okay, actually this one can use also in the classification, okay. In the classification, we use this another cost functions, okay. That is we call it a binary, but I think I already showed you that equation last week. Binary cross entropy. Okay, but this one is for the binary case. Okay, 0 or 1. Okay, but for that case, for the loss function for each symbol, we can calculate like this. By using the entropy equation. Okay, like this. And then for the cost functions, okay, is we assume that this one is for the one symbol. Okay, for the cost function, we can calculate by using 1 by the average, okay, the average of that one, okay. But anyway, this one, okay, let's assume that we have only one symbol, and this is our cos, our j omega, okay. And then if you find partial derivative of this one with respect to just a minute. Okay, so this will also give you this one. What is this? A minus I like this. Okay, so this is from the entropy, and then also there are other cost functions. Okay, but I will not cover them in here. Okay, you can study by yourself. Okay, so based on this cost function, for normally this one used for the classifications, and then this one used for the uh, regression. Okay, so based on that gradients, okay, to find the optimal, okay, what we have to do is, okay, what we have to do is we have to find the optimization, okay. Basically, the optimization is being to find that, as I mentioned in the first week, in this case, this is a cost. Okay, just a minute. I think I need to restart my computer. Okay, so please wait me. Okay, can you see my slide?
Yes.
Okay, so so as I mentioned in the previous slide, okay, optimization is being, okay, this is the cost. Okay, just a minute, okay. Okay, sorry about that. So to find the optimal, okay, basically what we have to do is, okay, so this is our cost function, okay, J omega, not omega, sorry, W, okay, and this is our W weight, okay, and then we need to change the weight, okay, we have to change the weight, okay, when we change the weight, okay, when we change the weight, okay, and this J omega, we have to find this one, okay, must be minimum, okay, so this is minimum cost, okay, because this is the cost. So that's it's been cost or loss or error. Okay, we have to find the minimum, the smallest error, smallest loss, smallest cost. Okay, based on this W. Okay, and then so we have to change that W. Okay, we have to change that W. Okay, and then find for each W, and then we need to find this minimum. And then we will use this W in the our model, our neural network to printed the other NO parameter. Okay, that we call as a optimization. Okay, so to find that one, okay, first what we have to do is we have to find partial derivative of that chord function with respect to W. Okay, but in this case we have many W, so this is meant for each W. Okay, W1, W2, W3 from the data 1 to 3 like this. Okay, and then we have to find out that one. Okay, and so in that case, for the error, we calculate like this. Actually, this one is the changes of the error of the cost function with respect to W. Okay, this is mean the slope. Okay, so the slope is mean the slope is mean, okay, the changes of, okay, so this is mean changes of that J omega, sorry, JW, okay, so that is mean this height, okay, and the changes of W is mean our width at the arc triangle, so this is mean actually that partial derivative is mean this slope. Okay, normally the slope, okay, so in this case, if your changes is like too steep, like this in like this here, okay, your this value, the partial derivative value of the error value will be height. Okay, the error will be height. Okay, and then one is right here. Okay, so this is mean the slope is a horizontal line. Okay, the error will be approximately equal to 0 because that slope is almost horizontal. Okay, but in the real case, okay, we cannot find the 0 error because we have to find for many templates. Okay, so anyway, to get this one, okay, so how we do is, okay, first we can start from the any location. Okay, we call it that we initialize W with the initial value. Okay, let's say in this case, okay, this is, let's say, the 5. Okay, 5, and then we calculate on the 5, we calculate this slope based on these equations. Okay, and then in this case, okay, that partial derivative, okay, will be greater than 0, and but it's quite high. Okay, and then what we do is from the current weight, okay, we decrease that error, that partial derivative in here. So that is mean as well move to new location. Okay, let's say this will be W2. Okay, W2. W2 is 5 minus, okay, this one. Okay, so it's 2. Okay, so this is W1. Okay, and then based on W1, we calculate that this slope. Okay, partial derivative. Okay, and then let's say we got greater than 0. Let's say we got 2, and then we, so this is W2. We find a new W, 5 minus 2. So that 2 is mean we got it from partial W, partial JW divided by W like this. And that is will be 3. Okay, so it will move to the new location 3. Okay, and then after that, we calculate the new derivative. Okay, like this. And then we find that W3. Okay, W2 minus that value. Okay, and if we initialize from here, okay, if we initialize from here, let's say this is W minus 1. Okay, in this case, if you calculate the slope in here, okay, if you calculate the slope in here, that is mean j w1 minus 1, partial derivative of jw minus 1, w minus 1 is will be less than 0. Okay, so that's why if we find minus 2, w minus 2, w minus 1 minus slope, it will be like the increase. So it will be moved to this direction. Okay, like this. And then finally we update like this. Okay, and then that j partial derivative value will be getting smaller and smaller. Okay, when this slope is getting like horizontal or getting like small, the slope is getting small, that value is getting small and small, and then finally you will end up in this optimal W. Okay, but if we calculate like this, okay, sometimes it will be too large, sometimes it will be too small. Okay, so in the real calculation, okay, in the next one I will show you to update our W. Okay, this is W from the previous one minus, okay, or some cases we just use a plus or minus, and then we use another parameter. Okay, okay, d minus 1. Okay, so we use this alpha. Okay, this alpha is mean we call as a running, landing rate. Okay, and that alpha will be control this increment or decrement step like this. Okay, you can control it. Okay, but what if alpha is equal to 1? Okay, that step is depend on only this gradient partial derivative. Okay, so as I mentioned that, okay, if we update by using this equation, if you do like this, okay, if we do like this finding point or this dot will be moving below or uh, like going down. Okay, that's why we call this method as a descent method, gradient descent method. Okay, this is very basic one and used in the many optimization. Okay, it's based on the first order optimization, first order derivative of the cost function. But the problem is this type of the problem we just call as a converse. Okay, because there's only one minimum. Okay, but in the reality, okay, it can be like this. We can have many minima. Okay, like this. So that is mean within this range, this is a minimum. This is a minimum. Okay, but if we compare all of them, okay, these two are not the minimum for the whole domain. Okay, that type of the minimum we call as a local. Okay, but in our model, okay, we want to find this global or the minimum for the whole domain. Okay, so if we use this gradient descent, okay, it's easy to implement, it's easy to update like this, but the problem is some cases, let's say if we start from here, okay, it will go down like this, and then in this case, the slope is almost 0, and then it will never go up again in here. Okay, so that is mean that W we can find in here is only not the whole minimum JW. This is the minimum JW respect to only this area like this. Okay, that type of the problem we call is a tract as a local minimum. But what we want to find is this one. Okay, so to solve this problem, okay, and in the neural network, okay, they has proposed many gradient variation of the gradient descent. Okay, optimization. Okay, so let's see. Let me write down that gradient descent calculation in here. Okay, so normally for the J omega, sorry, not omega, JW. Okay, if we have many sample, we can calculate like this. Okay, this I is this R minus W is R plus B square like this. Okay, and then we can calculate partial derivative of okay. Let's say we have in our model, okay, our network, okay, we have many W, okay, but actually we have to use R to index like this, okay. But let's say in here we have only one, okay. So this is we call it a gradient descent with respect to each WI, okay. And then in the gradient descent, okay, what we have to do is we have to find this gradient descent for JW with respect to all the W, okay, all the W like this, okay, and then we have to repeat that one, okay, and W we update it that W, okay, that I, okay, I has been any W in here, okay, we have to update all the I, okay, repeat for I start from the beginnings to all the weight or the neutron weight or sorry, or the linked weight, okay. Let's say this one minus alpha. This alpha is mean learning rate, okay, okay, multiplied with the partial derivative of J W divided by J W I. And then we have to repeat this process, okay, until this one is quite small, okay, approximately equal to 0. That we call as a convergence. Okay, we have to repeat like this. This algorithm, this optimization algorithm, we call as a gradient descent. Okay, it's only depend on this gradients, and then we line. We can start from the any locations. Okay, if we start from here, okay, that gradient will be greater than 0. Okay, so that is mean that W will be decreased. Okay, in this case, if you start from here, okay, that slope, that partial derivative, the gradients will be less than 0. This is mean that W will be increased. Okay, and then finally, this will end up in here. In that case, okay, so let me write down this one here. So let me write down as a gradients, okay, and this is a gradient, and in this case, the gradient will be approximately equal to 0. Okay, so that is mean we call it a convergent. We have to find like this. Okay, so this is the normal process. Okay, this is mean if we have 1,000 sample. Okay, we have to calculate the error for the whole 1,000 sample. Okay, and then find the average. Okay, find the average like this. Okay, and then based on that one, we calculate this partial derivative, and then we update this, repeat it again and again. Okay, that is we call it a gradient descent. But it's take time because each iteration we have to calculate all the symbols. Okay, and sometimes, okay, we may have many problems as I mentioned that okay, it's well tracked in the local minimum or something like that also. Okay, there's many problems. Okay, and one of the modification of the gradient descent that we call the stochastic gradient descent. Okay, so for this one, instead of we we use the whole symbol for one update. Okay, so this is the whole symbol. Okay, the whole symbol for one update. Okay, what we do is in this stochastic method, we consider each symbol like this, and then for the weight or the cost function, we just calculate it based on the each symbol. Okay, like this. Okay, so this is, let's say, WI, AI, YI. Okay, so I just refer as a one symbol. Okay, maybe. So please don't confuse this one with notes. Let me write online. This is referred to the each symbol. Okay, so that is mean for each symbol we update it the weight one time. Maybe let me write on this one as a J, otherwise you will get confused. Okay, this is a J. Here has been one symbol. Okay, and then after that we update it, that W, okay, T minus 1 minus alpha is, okay, this is calculated based on, let's say, calculated based on the symbol J. Like this. Okay, so that is mean for one symbol, we calculate the partial derivative for all weight with respect to all weight, and then after that we update it, okay, multiply with landing rate first, and we update it like this. Okay, so in this one is very efficient because some cases you don't need to run for all the symbols. Okay, you can find the convergence in the short time. Okay, and also you need the less memory because in the normal gradient descent you have to run the whole symbol for each iterations. Okay, but in here it's iteration. Okay, just one symbol. Okay, just one symbol. Okay, but in here for each iterations, okay, it's use the whole data set of the whole symbol like this. Okay, so that's why by using the stochastic gradient descent, okay, it's frequently updates, okay, just after one finish, so it can converge within the less time, okay, and less memory. But the problem is the gradients, okay, can be changed to height. Okay, it just means we start from here, okay, and then the gradient will be moved to here. Okay, because this is depend on the gradients, right? It can be moved to here or it can be moved to here like this. And then finally, it will never go to this local, global minimum. Or some cases even it's read to the global, but because of that, you have to run one by one, okay, the whole symbol or something like that. This can continue like this, okay. So that's why another option or another modification of the gradient descent is by using the mini batch. Okay, that mini batch is mean we have the whole data symbol, and then instead of by using one by one, okay, by using one by one, we make the, let's say, the group of, or maybe let's say the subset of the whole symbol like this. Okay, in here we have a group of the subset of the symbol or data set like this, and then for each subset of the data set we call it a batch. okay, that is group or is subset of the data we call as a batch. Okay, but we use a small, okay, not too large, not too small. Okay, not only one, maybe 10 or maybe 100 like this. Okay, and each batch or each group, okay, or each subset of the data, we by using that we update the weight. Okay, so actually this one is like we have the gradient descent. It's use the whole data. Stochastic gradient descent. We use a symbol, each symbol to update it. This one is middle. Okay, we make the group, not use the symbol. Okay, so like this. So in that case, okay, so this j omega pi is like this. Okay, 1 by, let's say m. Okay, m is less than n, and is the whole symbol. Okay, maybe divided by 10 or divided by something like that. It depends on the how many groups, how many batch you want to use this. Okay, and then we calculated that one I is equal to 0 to, or maybe start from the 1 m a j, sorry. Okay, j minus y j. Okay, and then we can calculate the partial derivative for each weight. Okay, this is our error of our partial derivatives, and then based on this one, we can update d is equal to r d minus 1 minus alpha s1. Like this. Okay, this one is based on the batch. Okay, a subset of the data. Okay, so that's why we call it a mini batch gradients. Okay, it's frequently updates. Okay, because in this case, this is the high fluctuation because it's just based on the one symbol. Okay, especially if you have the spike or the high different in your data set, or maybe spike in here. Okay, this gradient can be too large because this is based on the E symbol. Okay, but this one is just an average. Okay, so the step will be smooth. Okay, but this one is in middle. Okay, so that's why it's update frequently because of after one batch. So the data size for each batch is quite small, and then less variance because we calculate an average in here. Okay, so if you have the spike or error is being in the data, okay, it can mitigate because we calculate the average of the symbol. Okay, but it's also may get trapped in the local minimum. Okay, to solve that problem, okay, and we modify that optimization, the gradient descents. Okay, put it one more parameter that we call as a momentum. Okay, or another is like we can say that the speeds of the changes. Okay, we consider one more parameter. Okay, that we call as a gradient descent with the momentum. Okay, momentum was invented to reduce the high variance in the SDE. So it's a stochastic gradient descent, and it's also solving the convergence. Okay, so for the SDD, we can apply this momentum. Okay, and it's accelerate the convergence toward the relevant direction and reduce the fluctuation of the irrelevant direction also. Okay, so that formula is like this. Okay, in that case, okay, we consider one more parameter that we call as a momentum, and then that another name is, we can say that is a acute related speed. Or maybe we can say that the, sorry for my handwriting, weight okay, weighted, send off the past gradients like this. Okay, the formula for that one is that new parameter is MT. Okay, so this is being the momentum for the current time. Okay, it will be equal to, we have to use another parameter that control the momentum. Okay, and this is from the previous momentum plus 1 minus Peter partial L partial, or maybe let's say J W and J W T. Okay, so please keep in mind that this one is mean from the past, the previous calculation of this equation. Okay, and this one is the current gradients or current changes. Okay, we use this equation to calculate the momentum. Okay, and then in here we have to define this beta. Okay, we have to define that one. Okay, so let's say if beta is equal to 0.9. Okay, so 1 minus beta is equal to 0.1. Okay, so that is for this momentum updates. Okay, mostly it's depend on the previous momentum, and only 10% is depend on the current gradient like this. Okay, so that is mean we just change, we just control. Okay, we just control our changes or our gradients. Okay, actually not control the gradients. Okay, the contribution of the control there. Okay, let me write down like this. Okay, we can say like this: control the contribution of gradients. Okay, if the gradient is too high, okay, and we just use only 10%. Okay, so that is mean it will not affect to the changes. Okay, especially if like this case, okay, it's the slope is too high, so the gradient will be too large, right? Okay, too large, so we just reduce the speed like this, and then after that we update the weight. Okay, new weight, okay, is equal to current weight minus alpha, which is movement like this. Okay, like this. So in this case, you can control that current gradient's contribution by using this parameter, new parameter. Okay, like this. So by using that ones, it can reduce the oscillation, like this cannot happen, the changes of the gradients, the last changes of the gradient. Okay, even the gradient is too large, the update will include only a few or only the small percentage of the gradients. Okay, so it can reduce their oscillations. Okay, and high variance of the update. Okay, and it can convert faster than normal gradients like this. Okay, and another optimization method is we call it the adapted gradient descent. Okay, for that case, okay, instead of we use just only one alpha value, okay, we use the various type of the alpha value. Okay, at the beginning the alpha we use a large alpha, high alpha, and then after that we decrease the alpha value slowly after each iteration. Okay, that we call it an adaptive gradient. It's changing the landing rate based on the different weight during the training. Okay, because the alpha, okay, is too small, our updates or that each updates in the W. Okay, so sorry, this is a W. This should be the W. Okay, because this one I got it from the machine learning. Okay, from the machine learning. Okay, at the linear regression. That's why it's used as theta. Okay, but actually in our case, let's consider as a W. Okay, if too small, it may take time to reach here. Okay, if too large, alpha is too large. Okay, that changes will be can be the diverse or can go to the other location because the changes from here to here is too large. Okay, so it's moved from here to here because actually this is a weight update, right? This is D plus 1 current T minus the alpha, and even this changes is just 1. Okay, it will be depend on this alpha. If this alpha is like 100 to height, okay, from here it will go to here. From here it can go to here. So this will never redo this value. So that's why we have to find that suitable alpha. Okay, so basically how we consider it as first we use the height or large, okay, alpha, and then after each iteration, okay, we decrease, okay, decrease the alpha, okay, by using exponential or just the linear decreasing, okay, and one is getting close to the optimal or minimum value, the alpha value will be very small like this, okay, so it means it can go to here step by step slowly, okay, but as first it's fast and then after that is will get slow, okay, and another optimization method, okay, is also very well-known one, okay, is we call it a RMS prop, okay, this is mean the probable proportions, okay, so for this one RMS prop is mean we divided the learning rate exponential decaying average of the gradient as square gradients. Okay, so this is like this. Previously, we considered the data, okay, that to calculate the movement there. Okay, in this case, we have to consider another one. Okay, let's say either. Okay, this is actually okay calculated from there. This one. Okay, 1, 2, or m, okay, or maybe let's say multiplying with, okay, so that is mean all the weights, okay, we calculate the partial derivative of each one and then make it square, okay, and then we calculate one parameter like this, okay, and then after that we update the weight, okay, p minus 1 minus alpha divided by that theta, square root of theta, because this is a square, so make the square root first, multiply with a partial derivative of should be j omega respect to not jw, okay, with respect to jw. Okay, because it's updated with this one like this. Okay, so this is mean we just similar to that adapted, okay, but this one we just use the depend on the gradients. We made it square, okay, and find the square roots, okay. This has been actually the whole average, okay, and then made it square divided by that alpha, okay. So that is being also we just update the learning. We just adapt the landing rate. Okay, so it will reduce monotonically, decreasing the landing rate like this. Okay, so by using this one to eliminate the effect of sun gradient will be positive and sun will be negative. Okay, so this is one method. And another well-known method is a optimize attempt. Okay, attempt is being adapted moment with the moment and first and second order like this. Okay, or sometimes we call it a adapted moment and estimation method. This also. Okay, so in that case, actually it's a combination of this one and this one. Okay, so in that case, we need to calculate two. Okay, the first one is we have to calculate the moment. Okay, that's similar to the previous formula, beta 1 like this. Okay, and after that, we have to calculate another one also. Okay, this is the first moment. Okay, because there's no square. This is the second moment. Okay, so let's say this is a speed, this is a acceleration like this. Okay, and then in this case, this one you say beta 2 value. This is d, sorry, bt minus 1 plus 2. Okay, so this is the previous value. And in this case, well, like this. Okay, and then after that, the weight will be updated like this. Okay, so this one is we try to update or we try to reduce the alpha ending rate, like similar to this method. Okay, IMS Pro. Okay, and instead of using the gradients directly, okay, we calculate the momentums and then we control the current gradients by using the beta 1. Okay, so this one is the same as this stochastic gradient descent with the moment. Okay, so that's why add-on is mean combination of that two. Okay, so by using this method, okay, that's why it's quite popular. It's too fast and converts rapidly. Okay, and also it's rectify vanishing landing rate and high variance. But the problem is you have to, for each update, you have to calculate this too fast. So it's with the cost of the computational power. Okay, so let me summarize this one. So for the gradient descents, can be stacked on the local minima. Okay, solution for this is using the stochastic with the moment. Okay, which use the weight center of the gradient to help to get out of the local minima. Okay, but I will not explain this one. If you want to know how it can rid up or get out of from the local minimum, you can read it this thing. Okay, and another method, okay, is used to control the landing rate. Okay, at the beginning, it starts with a large number and then getting smaller and smaller. Okay, and okay, and then this one used to control the landing rate based on the square root of the gradient distance. Okay, and combination of that two, okay, Sorry, I got the overhooked my computer again. Okay, so this is about the gradient descent. Okay, so that's why in the neural network, okay, especially in the training, okay, we have to do both forward and backward. Okay, so firstly, what we have to do is firstly we have to initialize all the weight, okay, in the network, okay, randomly, okay, and then after that we have to calculate the forward propagations, okay, to cut this one or a to get the last output. Okay, and then after that we have to calculate the cost function that is being the error. Okay, and then based on that cost functions, we have to do the backward propagations. Okay, for backward propagations, okay, after we got the cost function, we have to find the partial derivative of that cost function with respect to is weight. Okay, the weight in here, let me define like that. J, K, L. Okay, so that is being, okay, this node is J, sorry, this node is K, and this is J, okay, and this is W, J, K, and this is the layer like this. Okay, so we have to calculate partial derivative of of them, okay, with respect to each weight for all of the weight. Okay, and then we have to multiply with for the normal, okay, gradient descents. We multiply with the landing rate, and then after that we update it. Then weight, sorry, T plus 1. Okay, and this is J, K, L, T plus 1. Okay, because this is the time domain. For the net weight, this is JK T. Okay, we have to update like this. And then after we update this, we need to check this value. Okay. And whether it is very small or maybe less than our target gradients. Let's say it is less than, okay, only this one is less than 0.00001. Okay, or some value, okay, you have to stop. Okay, and then some cases, because if we have to check every time, okay, it will slow down your training. Okay, some cases we just let it update, okay, and then we will check it after maybe 10 iteration, 100 iteration like this. Okay, and this is the way how we update the gradients. Okay, so it's already says, so let's take the break. Okay. For that, I will show you one numerical calculation. Okay, so currently let's take the break about 10 minutes. Okay, so let's meet again as a sys testing. Yeah. Okay.